Welcome everybody, kia ora koutou katoa. Welcome to the last webinar in the winter series. We've been running a webinar for the last 4 months, and today is our final one. The webinars, as you know, started due to our annual conference for 2020 being cancelled, but I can tell you now that the 2021 EEA conference planning is currently underway. So we're looking forward to you all joining us in 2021, either online or in person. It was a bit of a change going to webinars. We haven't used them before, but we've been really pleased with the commitment and feedback we've had from industry around the asset management webinars that we've been running. We've had fantastic feedback. And that feedback has really helped us each time improve the offering of the webinars. So for those of you who have been participating and giving us feedback, thank you very much for that. We've had some loud, clear messages that we'd like to do more face-to-face meetings as COVID-19 levels reduce, hopefully at some point to zero. So we're continuing to look at options for that. We're absolutely delighted at the calibre and quality of the papers that have been offered for the webinar series, and I'd just like to acknowledge today's speakers. Some fantastic issues are going to be covered, so really delighted to have such high calibre papers and such high calibre presenters here today. I'd also like to acknowledge our partner, the Epicentre. It's been great to have them on board. It's been an opportunity for us to engage with our students and future engineers for the industry. So really pleased that Epicentre has been able to be a partner in these 4 webinars. The last 3 webinars, we've had almost 200 people attend, and as I said, we've had great feedback. And today's webinar, we've got 60 plus who are attending today as well. Today's webinar, we're looking at asset projects, and we're going to cover off, I think, some pretty critical topics. If you look at where energy policy is heading, it's around things like batteries, it's around things like electric vehicles, and it's around things like better management of our existing assets. We spend about $1 billion a year on assets, either in terms of building of new assets or replacement of existing assets. So the use of projects and project management is something that is really absolutely critical going forward for our industry. So what are the key elements to a successful project? The common elements I see are planning, getting the right people together, strong teamwork, strong communications, a good risk management focus, and making sure we get strong project closeout. Planning is about understanding what's required and ensuring that there are enough resources. Having the right people is a real challenge for the industry at the moment, given the volume of work that we've got and the fact that our reliance upon a number of overseas consultants has been stopped because of the COVID issue. So we've got some real challenges around today's complex projects and getting the right people for that. But it's heartening to see that industry is stepping up in these areas, and we are starting to deliver and continuing to deliver really good projects. Communication is really critical. It's about engaging with stakeholders and our customers to ensure that their expectations are managed, and that we don't end up having to rework because our customers and our recipients of these projects aren't getting what they required. One of the big challenges we've got is around understanding project risks. One of the issues for the industry at the moment is just the sheer volume of change and uncertainty that's going on. So really looking at project risk is going to be absolutely critical. And that risk can be a technical risk, that can be a stakeholder risk. So really understanding those parameters is really important. Finally, closing out the project. With a lot of projects, it's down to getting those last little bits and pieces done that actually completes the project and enables, if you like, the turnkey to be handed over and the project to be, and the equipment and processes to be up and running. We've got a number of critical projects that are going to be talked about today. As I said, they're all in the topical areas. So I'd really like you to enjoy the presentations today. I'm certainly looking forward to them. There'll be lots of really good learnings and insights from each of the presenter topics. If you've got questions, I'd encourage you to put the questions through on the Q&A function that's there, and we'll endeavour to answer those questions as either as part of the Q&A time, or if we're not able to do it on the Q&A, our presenters will type in a response that will go onto the Q&A function there for attendees to review. I don't get to say anything more after this, but before I hand over to Paul Blackmore, I just want to acknowledge the work that Sean and the Epicenter team have done in terms of setting up the 4 webinars. As I said, it was greenfield stuff for the EEA, but Sean has taken the bull by the horns, so to speak, and has really driven some great outcomes. So Sean, on behalf of the EEA team and the EEA members, thanks very much for all the work that you've done in setting up these 4 webinars. It's now my pleasure to introduce Paul Blackmore. Paul is Fleet Asset Manager at PowerCo, and he's a member of the Asset Management Group. And Paul will be the moderator and manager of the forum from now on. So Paul, hand over to you. To all of the recipients, enjoy the time you've got today. Think about the challenges that are going to be put in front of you, and come up with some really good questions to challenge our presenters. So Paul, over to you.
Thanks very much for the kind introduction, Peter. And just to say it one more time, please put your questions into the Q&A panel, and we'll get to those time permitting at the end of each speaker's turn. So our first speaker today is Eric Walters, a consultant in the electricity distribution sector. Eric's going to talk to us about implementation of Whangamata's standby battery energy storage system. Eric Walters is a chartered professional engineer with more than 35 years of experience across power generation, transmission and distribution sectors. In former roles, he's acted as the owner's engineer and lender's technical advisor on mega renewable generation projects in Asia and Israel. For the past several years, Eric's been working as an independent consultant in New Zealand's distribution sector. The paper Eric will be co-presenting this year draws on his experience as owner's representative and project coordinator on PowerCo's recently commissioned Whangamata Battery Energy Storage System, BESS project. So over to you, Eric.
Great, thanks, Paul. Look, first of all, I have to give you Gabriel Lim's apologies. He was going to join me for this presentation, but he's looking after sick kids at home. Bit rough in the school holidays having sick kids, but I'll cover his slides. So it's been said that experience is not something that you get until just after you need it. And in New Zealand, we don't have a lot of experience in backup battery energy storage system power supplies. And so when PowerCo embarked on this journey for its first one, it didn't have many resources to draw upon within New Zealand. And that led to some decisions being made around contracting strategies that have worked out for us, but could perhaps have been better. So let's go through and I'll share some ideas that we have. So first of all, I'm going to talk about the background to the project and the use cases that it was designed for. Then we'll talk through some of the contractual arrangements, the lessons learned, and finally go through some of the questions that have been posed. So Whangamata is a resort town on the coast in the Bay of Plenty. During holiday periods and special events, the population can swell from a few thousand permanent residents to several tens of thousands. And the annual beach hop, which is in the pictures shown, can regularly attract 100,000 visitors. So Whangamata's economic health relies on a reliable power supply, and its business community is dependent on that holiday custom to survive the remainder of the year. So Whangamata is fed by a single 33 kV circuit that runs over the hill from Waihi. It runs through some pretty rugged bush-covered country, and it frequently drops out because of vegetation interference on the line. And that can take out the whole area through from Whangamata to Onamana out to Potri. Pauco, in consultation with the business leaders in the Whangamata community, decided that the best way forward was to put a battery energy storage system in place, coupled with a diesel generator to provide backup power. And this was because it was going to take a lot of effort to put in a 33 kV line. It could have taken quite a long time, given the consenting issues that it would have faced, because a lot of it goes across Department of Conservation land. So we ended up with a battery energy storage system. Just pointing out, I don't know if you can see my mouse, but in the picture you can see the diesel generator at the top of the picture, and you've got the battery container sitting to the left of the upper part of the facility, and then you've got the power conversion system, the inverters, sitting in the container in the middle, a step-up transformer, and in the portacom you've got your 11 kV switchgear. So it was intended to be used for dynamic islanding. So essentially, the battery is connected to the network. The network, fed from the 33 kV system through a couple of transformers, feeds the CBD through this Hetherington Road feeder. If the storage management system detects a loss of voltage on the 33 or the 11, it opens the circuit breaker and the battery continues to feed the CBD of Whangamata. It wasn't intended to feed the whole of the town. It's only rated for 2 megawatts, which is enough just to feed the CBD for about 2 hours. And if the line hasn't been brought back by then, our operators have the option of starting the diesel generator. So besides dynamic islanding, it's also used for scheduled islanding. So just last or 2 weeks ago, we had a crossarm that needed replacing on the 33 kV line, and we used the battery and the diesel to feed a substantial part of Whangamata for the time it took to do the repair. So we also used for peak shaving during summer months when during hot weather and when the town is highly populated. It's useful for knocking off the power peak to reduce the loading on the transmission lines. Also use it for dynamic voltage support, and if absolutely necessary, we could black start using the system. Okay, so in a typical EPC contract arrangement, the arrangement's designed to put responsibility for design, procurement, construction, commissioning, and guarantee for performance on a single contractor or a consortium of contractors and investors. Now, whether or not this entity chooses to use subcontractors is immaterial to the purchaser. It expects the entity to deliver a fully functional solution, compliant with whatever technical specs have been agreed upon, and to guarantee its performance. Now, EPC contracts are a useful vehicle for managing of risk, both from the perspective of the purchaser and also any project financiers. The EPC contractor will enter into back-to-back liability agreements with its individual suppliers and subcontractors in order to manage its own risk, and it may enter into supplementary insurance arrangements to cover its own portion of the risk. It's not uncommon for the EPC contractor to also be one of the participants. So an equipment supplier, for example, equipment installer, or even the designer may take the EPC role in one of these contracts. I've been involved in 3 geothermal projects where the equipment supplier was involved. Soldo for the Salak geothermal project, Fuji at Kawerau geothermal plant here in New Zealand, and Mitsubishi on another project in Indonesia. The installer was involved on the Derajat 3 project in Indonesia. That was TEAS from Australia, and on the Derajat 1 and 2 it was the designer, Stone and Webster. On the Namthun 2 hydro project in Laos, I was Lender's technical advisor. EDF was the EPC contractor and the owner's engineer. Through Chinese walls, they were able to manage it, and part of our role as the Lender's technical advisor was to make sure that there was no hanky-panky going on, but it worked well. The owner's engineer role is typically there to keep the EPC contractor honest. So it's to monitor that the contract is being complied with, the technical specification is being complied with, that the quality controls are in place, that the project controls are in place. In FIDIC, it's referred to as the owner's representative role, and in FIDIC, the owner's representative has a few more powers than the owner's engineer. And then you've got the LTA or lender's engineer role, which may sit alongside and act as a secondary monitor of EPC performance. So that's a typical EPC contract. Now, PowerCo decided they would like to go with the EPC route because they didn't have a lot of experience in battery energy storage systems, and they also wanted to manage their risks. But what we ended up with was actually quite a complicated contract structure. And Electropower told us, well, that's not really an EPC, it's a hybrid, and they're probably right, because we employed Electropower PLP to be the EPC contractor. They were dealing with S&C Electric out of the States, who were doing the system integration design and the battery system supply, including the inverters, which is an S&C product. ETEL provided transformers, Portacom provided the building, Combella did the civil engineering. Combella's an Australian crowd. North Power did the installation and site works. But separately, PowerCo was employing North Power to do the enabling works and the diesel generator installation. We sourced the diesel generator directly from Goff, and the switchboard, the 11 kV switchboard from Siemens. SEL relays from SEL, AECOM does the balance of plant design. So there are a number of contracts and interfaces running. We tried to push as much of the interface management onto Electropower as we could, but they will be the first to tell you it was difficult to manage all of those interfaces. Now, the problem was that there were a number of problems with this contract arrangement. The first being that there was a lot more technical oversight from PowerCo than we anticipated, and we also incurred a risk premium of an EPC contract without enjoying the full benefit. That was one of the lessons that we learned. So going through to the lessons learned for us, for PowerCo, it was a complicated contract structure. It led to some resource conflicts, especially when we're trying to manage limited North Power resources. There were a lot of fait accompli decisions. So once having committed on the path with S&C, there were decisions that needed to be made partway through the contract. For example, securing a manufacturing slot for the inverters and battery management systems. The contract should anticipate that suppliers like S&C will be protective of their IP. So it kind of again leads to another fait accompli decision on we need to use S&C for our operations and maintenance for the next few years until we've at least got some experience under our belt with this technology. There were quite a few unanticipated cost escalations in this contract as well. On the plus side, factory visits were worthwhile. I went twice to Milwaukee to visit the factory and see what they're doing, get progress updates and witness factory tests. It failed one factory test, which had to be redone at a later date. The site was managed well. There were no LTIs, no lost time incidents. Good working relationship between me and the EPC contract PM, Alan James from PLP Electripar. It felt like we worked in partnership to make the project happen, and it's good to have those sorts of working relationships. We set up a governance group consisting representatives from PLP Electripar and senior managers at PowerCo, and it was useful for those regular meetings to raise issues that the project was experiencing and resolve them in the meeting itself. And I have to say it was crucial to involve operations quite early, and I'll get into that a little bit further. So operations, the handover process, we had to think about all sorts of things, including operational readiness. Our operators aren't used to running generators or generating sources. They're used to switching in distribution networks. We had to think about the maintenance and engineering. We had to think about documentation and how to involve the community in what we were doing. All of this were facets of the handover. We had to involve our health and safety team just to make sure that it was being set up correctly and safely. So good to start that process early. You also, need the operator's involvement in the interface design, the control system design. So lessons for the industry: that the contract structure does have a significant influence on project performance. EPC in this case is not necessarily the best choice for a bespoke application, especially when you've got high tech involved. Instead, you might consider using an independent system integrator. So this is a company that will do essentially the design for you, and then you would go out to tender with their design for the various components of the system. So here are some examples of alternative contract structures to the traditional EPC arrangement. So you might have the purchaser, the owner engineer, a system integrator acting as the EPC contractor and taking EPC risk, managing the back-to-back liability obligations of the various subcontracts. Alternatively, the system integrator might not be interested in taking a risk position on the project, and so you could have the EPC contractor managing a system integrator and the engineering, procurement and construction contracts independently. Alternatively, an EPC manager is a consultant that you would employ to manage the whole process as if he were an EPC contractor, but without the EPC risk premium. And in this case, the purchaser would be entering into direct contracts with the system integrator, the designer contract. Go back to that slide. And the EPC manager would be managing each of the interfaces with these. Finally, the idea would be to go to very early on in the process, choose an appropriate contract strategy that addresses how the project risk is to be mitigated, the costs allocated and the suppliers held to account. You might think about whether to go to tender or sole source. Sole source has the advantages that if you've got a relationship going and you have and you can trust the supplier and they have a good reputation, it can be a good outcome. And you can actually achieve a lower cost because the EPC contractor doesn't need to price in for some of the usual contingencies that he would if you were tendering. But on the other hand, you get some competitive advantages if you're going tendering. I probably don't need to tell you guys this. Do appropriate due diligence on your contracting parties. Look at their technical depth, whether they have a history of going to court after projects or during projects, how they're managing their risks and liabilities, their back-to-back contract arrangements and structures, their intellectual property protection, and whether they're in a position to provide good after-sales support. And lastly, make sure you involve operators early because they need to be involved in the training and handover. So in summary, I'd say that PowerCo didn't get a bad outcome from this project, but it may have got a better one if it had, with the benefit of hindsight, thought through the contracting strategy when it was framing this project. Okay, that's the end of my slides. I'll just flick over to the Q&A to see if there's been any questions.
No questions at this stage, Eric, but I might ask one if I may.
Sure.
You mentioned there was a lot of fait accompli decisions, and I imagine those are quite difficult to predict. But any thoughts on strategies for heading off or dealing with those fait accompli decisions which can arise?
I think planning the contracting strategy you're going to adopt before you actually embark on it. So in this case, when we engaged S&C, or PowerCo engaged S&C quite early in the game to be their advisor, and ultimately S&C became the preferred supplier, and then PowerCo had to commit to a manufacturing window before the design was actually complete. So if we'd decided on a contracting strategy early on, the steps would have been completed in logical sequence, and I would have avoided the need for some of these on-the-fly decisions that pretty much had to be made.
Cool. Well, thanks very much for your presentation, Eric. I'm sure there's some learnings for the whole industry out of that. Right, we'll now like to move on to the next presentation. Our next presenter is Feng Wu from Transpower. Feng is going to talk to us about substation outdoor bus support structures, asset management challenges and experiences. Feng has over 9 years experience in New Zealand's power industry. Feng joined Transpower in 2011 after graduating from Auckland University with a Master's in Engineering. He's held the role of Delivery Project Manager for leading major and minor capital works of various nature in Transpower substations before joining the Asset Management Planning team in 2016, where he's been involved with developing long-term asset management solutions for substation assets. Feng is a CPEng and currently holds PMP certification. Over to you, Feng.
Thank you. So today I'm going to briefly talk about the experience that we have gained so far about managing our substation assets, especially around the structures and buswork assets, which I'm looking after, and I'll share a bit of challenge that we have faced. So the structure of the presentation, basically, I'll cover a bit of the background, the context information about structures and buswork and the issues that we've been facing. And I'll move on to the UAV condition assessment, where we have trialed a couple of times with drone inspection for station assets, and then moving on to the asset information work that we've been working on. And then lastly, I will touch on briefly about the health modeling as well as criticality framework we've been working on as well. So I'm pretty sure most people will be familiar with the sort of substation and what is bus structure, but I'll just cover here briefly. So a typical bus system will have a bus conductor, then you have insulators, and then you have your support structures. In Transpower, the 110 and 220 kV structures will use lattice gantries as the support structure for the strong bus work, and we use the concrete support posts for 220 kV rigid bus systems. So the photos on the left-hand side, they are 220 kV bus systems. The top one is the strong bus, and the bottom is rigid bus work, and to the right, it's 110 kV strong bus system. And this is another generation of the design that we have. The modern design of the 220 kV strong bus will use A-frame gantry and steel post and aluminium bus bar for the rigid bus system, whereas for 110 kV, we're using the I-beam as the gantry structure rather than lattice gantries. In terms of asset population, we've got about 1,500 of the structures and girders assets in our network for both 110 kV and 220 kV, and 90% of them are lattice structures. And with respect to the support posts, we've got about 10,000 support posts, and a lot of them are concrete support posts. In terms of drivers, age is one of the biggest concerns for us, is that by 2020, which is this year, we've got over 40% of the structures and buswork assets are over 50 years old, which is their design life. And then by 2025, we are forecasting over 80% of them will be over 50 years old. And the second element of the driver is that the natural degradation of these aging assets. Although a lot of the structures and buswork assets are in pretty good condition, but we do see some degradations to a various degree in different substations. And a lot of the issues are localized corrosions on the gantries as well as on concrete support structures. And lastly, we want to make sure that we provide reliable power to the New Zealand power system by managing our asset risks with aging assets correctly and appropriately. Just a few photos showing the worst side of the asset condition that we've picked up. So the typical condition issues that we have, for steel lattice gantries for both 110 kV and 220 kV ones, the localized corrosion under the armpit of angle steel is pretty common. Another common of corrosion issues that we have a bit of corrosion underneath the base plate and the grout as well. With concrete support posts, which we use a lot of them for 220 kV rigid bus bars, at some sites we'll start seeing spalling of concrete, one on the secondary reinforcing, and the one that's more concerning is the major crack alongside the main reinforcing bars. So in order for us to make effective asset management decisions, the critical elements are, the first one is that we have the right and accurate condition information for all our assets so that we can use them to assess the risk of failure and the intervention options. The second one, we want to understand the long-term trend of the asset condition over time so that we can foresee the amount of work that we will have out in the future. And thirdly, we want to understand the criticality of the asset if it fails in terms of different dimensions, which I will briefly cover later on in the PowerPoint. And lastly, based on the information that we have, we want to identify the best interventions for managing these asset conditions. So moving on to UAV or drone inspection. So talking about the condition assessment, for structures and buswork, we are heavily relying on visual assessment. So we typically use ground inspection, where you have condition assessor working around switch out from the ground level and note the defects and condition problems with the specific asset. And then we have periodic out of service inspection, where we do more extensive assessment on the assets and identify the defects. And more recently, we brought in climbing inspection by using Transpower's line condition assessors, because corrosions on towers is not too dissimilar to corrosions that we have on steel lattice gantries. And the lastly is what I'm going to talk about is the using drone to help with condition assessment. So we did a couple of trials of using drone for condition assessment at one of our training facilities down in Hungley. And we have, so the trial is really trying to understand what we can use the technology for and what technology can offer. And more importantly, it's a sort of proof of concept for us to use drone technology in a substation environment. And we are also trying to make sure that we manage the risk correctly. So we have tried 3 different drones. So from top down, the first one is DJI Mavic, which is the smallest one, which is about 168 millimeter from end to end. And the middle one is a DJI Inspire, and the last one is reasonably larger drone we use, which is the Matriz 600, which is about 1.7 meter from end to end. Talking about risks, risk management for using drone in station environment. So I've put the main risks here that we have focused on to manage. So the first one is safety. So for managing the safety risk, we want to make sure that the competency for the people who is doing the condition assessment are meeting Transpower's requirements. So this includes to make sure that the pilot has the correct competency for operating the aircraft, as well as the supervisor who will be doing the supervising has the correct competency to do the supervision, as well as have correct Transpower competency to work in the substation environment. And then we want to make sure that the planning is robust, as well as the communication with different affected parties. So this includes the our incumbent electrical service providers to understand if they have any planned work at the same time where we were planning to fly drone over, as well as with transports control centers to make sure that if they are to make aware of any outages on the same day on site. And we want to make sure that we have dedicated pilot and camera operators so that each one of them have their own job to focus on. So loss of control is the technology is the big part, and here we want to make sure that technology is fit for purpose, and we've got GPS and RTK and programmable return to base, and then a bit of some sensors sending back the critical information of the drone. And in terms of process for risk management, we want to make sure that equipment are checked and maintained, and we have planning, and we're maintaining line of sight at all time. And moving on the collection into equipment, so they are mainly around the flight path planning, the operating the UAV within the limit, as well as we don't want any fly under any conductors. In terms of risk of loss of load, we've decided that we want to make sure that the site is maintaining N-1 security at all times during the mission, and public perception mainly around communication with the neighbours through letter drops or conversations, and make sure we put up the PPE, we put on the PPE and the signages, and we fly within the substation boundary. So here is basically a whole list of planning activities we typically do. I won't go through every single one of them, but the key thing is that we want to check the weather forecast on the day, the outages, and we make sure that we do the risk assessment. So these planning activities need to be done before the day, and on the day, just prior to flight, we want to make sure that all the staff members are fit and they understand what they are doing on site on the day, and put on a signage and talk with other work parties if there are some, and check for hazards and walk through the plan, and make sure that we identify nearest live points and do the pre-flight checks on the equipment. And during the flight, we want to make sure that the aircraft is constantly in the visual distance, and the aircraft is fully under control, and there's no abnormal signals coming back from the aircraft. We want to make sure that we have enough batteries reserved for us to go back to return to base, and there's nothing in the middle of the flight path of the return to base. So this slide is the flight path planning for the first flight. So the one on the left, basically the flight one where we are taking the grid photos of the substation. So H is the home, basically where it take off and where it lands. And point 1 is starting point of the flight, and point 2 is the end point of flight, and we just do a grid zigzag around the station. And with the image, we basically can do a stitched up photos, which is on the right. And the flight 2 is around condition assessment of the gantry. And basically that's how we sort of plan for the flight. And the one on the right is the proposed flight path to take good pictures of the girder. In terms of results, the image we get back are pretty good actually. So here are just a few examples where we were able to pick up the details of defect on the components of the asset, which we can't really inspect from ground level. So the top left corner is just showing the disconnector, the rusty bolt on top of the insulator of the disconnector, and the left bottom just showing a few rusty nuts under the underside of the steel angle steel, which is about maybe 10-15 meters above the ground. And the right one is the just showing the stem or the pin of the string glass insulators, just showing the rust here. And the bottom one is showing the building roof, where you can see on the zoomed in photo where there's a rusty bolt head sort of covered under lichen on building roof. So the key benefit of using drone is that we can assess pretty much all the outdoor assets that cannot be seen from the ground level, and with great image quality, and we can take photos from all sorts of angles. And the other benefit is that we doesn't really need outage, and actually we want to have everything in service. just from risk management point of view. And with the image we have taken from drone, it's very easy to verify any questions around condition scores we put in by just going back to the photos. And by doing this, we get rid of the climb inspection for some sites where we don't. We get rid of the risk from working at height. And with drone, which can cover the whole site, it's been cost effective as well. And the last point is image processing. So if we have enough photos showing the defects, we can potentially use that to train up AI to help identify the condition assessments and defects rather than having people going through the photos manually. The key learnings and challenges that one of the learnings that we want to use the bigger drone. We have tried 3 drones, and the bigger one turned out to provide the best quality because it has better stabilization as well. That means we can put more powerful camera on drone to take better photos. Not all sites are suitable to use drone from risk management point of view. So as I said, the drone, we probably won't fly drone for insecurity sites just for a risk of loss of supply in case of drone clash into equipment. It's quite weather dependent as well, so it needs to be, the weather needs to be reasonably fine. It doesn't have to be perfectly beautiful, but the wind, the limit, and visibility is 2 of the key critical elements. And we do require a specialist service provider here. And planning and risk management is quite a lot heavier than ground level inspection or climate inspection. And another challenge is the image storage, because each photo is about 20-30 megabytes, and they all add up quite quickly. So moving on to asset information. So with asset information, the main 3 elements here is that a hierarchy and grouping of our assets so that we can assess them easily, as well as we can store our condition scores and asset attributes properly to the right asset. The naming standard is quite important as well, so that the assets can be searched reasonably quickly, and running a report will be easier with standard naming conventions. And lastly, the meters and attributes of the assets, which basically the condition, what kind of condition score we want to capture. So in terms of hierarchy of and grouping of the assets, a few general principles in terms of design of the hierarchy. The most important one is it should be a logical grouping of the assets by location, so that they can be easily identified and correlated back to site when the guys are on site doing condition assessment. And the way that we want to design assets so that if something fails, we can tell what is the consequence of failure from the service delivery, from the service performance point of view, as well as from the safety point of view. And we want to provide reasonable granularity so that we can use them for scoping up the job, for inputting to the health models and to predict the future trend, as well as to figure out what are the best intervention options. And lastly, we want to capture all the key assets in our asset information system. So this is a Strand bus work asset structure. So the key assets we are capturing here are the girders, which are the horizontal beams, the conductors and insulators. And the way that we have designed it is so that we have device positions and assets. So device position is basically a location holder, which holds assets under the same location. So in this case, as an example, girder 66 device position would have the girder 66 asset, the insulator set asset, for the horizontal one, as well as the jumper insulator under the device position. So similar concept applies to the insulators, to the conductors. And here is a example of a rigid bus system. So where we use disconnectors as the demarcation points or sectionalizing the bus. So the one on the left is single line diagram, and the one on the right on the photo is actually the physical asset representing the single line diagram. And we have bus post device position where we have post asset as well as post insulator and the conductor asset. And this is just another example of the rigid bus section. Another important one, as I mentioned before, we want to understand the consequence of failure if a insulator fails or if a dropper fails or conductor fails. The way we do that is that we are associating these physical assets, the insulators, the conductors, and the girders and structure asset with the bus system that we have. So under the bus system, we can see a group of components under the bus section. So which in turn we can figure out the outage blocks links to that components, and by which we can understand the service performance, or if there's any power system collisions. Meters and attributes. So meters are basically the condition assessment information we want to keep. In terms of the design principle for that is that we want to make sure that we capture the accurate representation of the condition of the asset. And then we want to be able to use that meter information to understand the risk of failure and the failure modes, and then help us with intervention options and cost estimation and all that. So to do that, we have put together a condition assessment guide with photos, and we have introduced the condition bands from 1 to 100, and we split the 1 to 100 scoring into 10 condition bands. So 1 to 10 being the worst, which meaning that we have to do something really urgently, otherwise it's going to fail very soon, and 100 being brand new. And the way that we record the condition is that 2 ways. One is that we record the quantity under each of the condition bands, such as 20% of dots is under condition 11 to 20, so that we can use that for scoping purpose, or for smaller assets like insulator assets, we just record the worst condition insulators. In terms of attributes, which is basically the asset features, we want to capture the information about the design, whether it's lattice gantry material, or is it steel or aluminum, or is it concrete, and the type, is it a lattice gantry or is it A-frame gantry, and the voltage the structures are supporting. And this is just some quick examples of the things that I just discussed before. So in terms of, for lattice structures, we're capturing the bolts, the minor steels, the main steels, and the foundations. Support posts, we basically count the post, say 5 posts under 10 to 11 to 20, and there's another 20 posts under 20 to 40, say. And that applies for each of the section that I was describing before. And conductor and insulators, they are basically we're capturing the worst condition. And the last one is spatial mapping. So what we have been working on is that we're trying to convert the single line diagram, which is very easy, very simplified version of the power system, and we want to translate the bus sections and overlay a layer to our spatial map, so that we can understand if we were going to work on any of the girders, we know which bus section in our asset maintenance system is affected, so that we can, at the planning stage, we know the system impact and the risk associated with particular work. So I'll do a very quick touch on health modeling and criticality framework. So what we use here is that we use asset health index, which is scaled from roughly about 0.5 to 10. So 0.5 being brand new, and 10 being the high risk and really poor condition assets. As in the model, we use a few parameters. One is the nominal asset life. Say structures will be design life of 50 years or 55 years in the current age, and then we combine with the location or information which link to the corrosion zones, different corrosion zones that we have in transfer, and combine with current condition. And maybe there's an option to add on duty on how heavily the structure is loaded to the equation to understand the asset health. The chart at the bottom is basically showing the current snapshot of the asset health index overall, just as an example. So I mentioned about the corrosion zones. We have 6 corrosion zones for transmission lines, and we proxy these corrosion zones by using the nearest tower and use that as corrosion zones for substation. And then we have steel lattice gantry degradation curves, which for each of the corrosion zones on the left, which we use to estimate the condition of the gantry based on the age as well as based on the corrosion zone. So table on the right basically the expected life of the steel lattice gantry. So apologies, there's a typo. It should be steel lattice gantry rather than composite. And as you can see, the expected life at different corrosions, they vary quite a bit. So at benign, we're expecting over 100 years out of structure, whereas in the extreme area, it's about 20 years or 18 years. And we've got degradation curves for insulators as well. I'm just conscious of time that I'm sort of running out of time. So, and with criticality, so we're trying to monetize the criticality if something fails by using the most likely failure mode, and then we try to estimate the criticality or the consequence based on 5 dimensions. So that includes public safety, the workers' safety, the service performance, which is basically loss of load to the system, or maybe in the future we might add on the loss of generation, and the environment impact, as well as the direct cost to replace the asset as criticality. And the key challenges with criticality and asset health modeling, I think the main one is about predicting the degradation of the assets. There are a lot of variables in here that will affect the rate of degradation. So the macro environment is one of them, which is the corrosion zone, and the meso environment, the local environment, the structures or the assets exposed in, like humidity, the prevailing wind, and the pollutions and other key influence factors. And then lastly, the microenvironment, such as how the structure is built. For example, I use steel gantry as an example. The area on the top where it's exposed to the rain and the sun normally has better condition than the armpit, because under the angle steel, under the armpit of angle steel, the salt deposit cannot get washed away, so that they tend to corrode a lot faster. And then lastly, construction variables, which is very hard to predict. So it depends on the material quality, the zinc thickness, if there's any damage during the construction. For concrete assets, the concrete quality and the construction of the concrete supports is a big influence to the degradation rate. In terms of criticality, the challenge is about trying to understand the failure mode and the impact. So we had to make some assumptions around what is the most likely failure and what's the most likely impact. Cascade failure is another one that's difficult to predict. And in terms of the system performance, the value of load, and we use average value, but ideally we want to be able to use, depending on the power system configuration at the time, this different value to the load. So that's the end of my presentation.
Cool. Thank you very much, Feng. There's no questions come through on the panel, so if anyone has one, please ask quickly. But in the meantime, I'd like to ask one. Firstly, congratulate you on the level of detail you guys are getting to in breaking down your asset structure and recording meters against individual structural components. That's very impressive. But I'd just like to ask you, over time, I expect you'll be generating a lot of photographs. So can you talk to us about, tell us how you would be managing those photos and the history so that you can keep track of them and access them in the future?
Yeah, I think the one we store a lot of photos in our network drives. It's not really ideal, and the amount of photo that we are taking, we have got to point. I suspect it may be too many to manage. But in the future, what I expect is that we only want to keep the photos where they are clear condition issues, and then another way to help with managing the photos is that we could potentially, rather than doing a periodic inspection, if we can have a good enough health model to predict the potential next intervention time, then we can just work back and do another inspection back in them. Just do it as a need basis. That will help us to reduce the photos by quite a bit. But I think photo storage is another big challenge of all, because we can have a lot of data, but we have to find a way to manage them and store them and search them. That's a big challenge, which Transpire is working on at the moment as we speak.
Cool, thanks. Thanks, Feng. There's another question from Chris Knight. He says, in addition to the 4 metre clearances all times, I think you mentioned no fly under conductors. Curious as to why under is a restriction rather than over.
So to answer the question, it heavily linked to the how we program the emergency landing of the aircraft. So we have, if you can recall, we have a function of return to base under emergency. So by default, a lot of drones are return to base. The pre-programmed is that the drone will go vertically up to a very, very high level, and then transit to the base. If you fly the drone under the conductor and there's emergency response which triggers return to base, it'll just basically hit the conductor.
Okay, understood. Thanks, Finn. One more question. I think this might be, there's probably time for one more after this if there's one. Thanks for the comprehensive presentation. Regarding UAVs, are there any assurance from DJI or other manufacturers regarding failure modes, i.e. would a single blade failure or control system failure cause loss of UAV potential strike into the structures? I guess that's down to that mission criticality of flying nearby live substations.
Yes, so in terms of the equipment selection, I think there's a requirement where we require that the drone has a backup motor. So if one motor fails, it will cause the drone to become uncontrollable. So that's one of the measures, and the other one is to prevent the consequence failure if should it hit a conductor. So which is managed through by maintaining the site and minus ground security at all time. With the size of the drone, in terms of the equipment damage, when it hit onto one of them, most likely the drone will get damaged, whereas the equipment is probably not get as bad damage from the hit.
Very good. Right, thanks, Finn. All right, I think we have no further questions, so yeah, thank you very much. I'd like to now move on to our next and final presentation, who is from Cherie McNabb from the Epicentre at Christchurch. Cherie's going to talk to us about opportunities for repurposing EV batteries for stationary energy applications in New Zealand. Cherie is a research engineer at Epicentre, University of Canterbury. Currently, she's exploring probabilistic modelling of the impact of electric vehicles on distribution networks and has research interests in battery technologies and the circular economy. She's worked on the Green Grid project, exploring the impact of distributed generation analysis of the economic benefits of DER technologies for homeowners. Cherie was a research staff member at the Nanofabrication and Exploratory Devices Group of the IBM TJ Watson Research Centre in Yorktown Heights, New York. She has also worked as a system requirements engineer for Allied Telesis switch and router portfolio. Cherie McNabb holds a PhD and first-class honours Bachelor of Engineering degree from University of Canterbury. So over to you, Cherie.
Thanks, Paul. Good afternoon. Today I'm presenting a project on looking at the feasibility of repurposing electric vehicle batteries once they come to the end of their life and motive applications for stationary battery energy storage applications. This work was conducted by Cheng Zhang, who was a student in the Masters of Engineering, who I supervised. Just also like to acknowledge the sponsorship from Dark Technologies, a local Christchurch technology company who proposed this topic. So just an outline, today I'm going to give some background about the different battery chemistries for energy storage. It's also look at the landscape of battery energy storage applications, see if the lithium-ion batteries used in EVs are going to be suitable for those applications, and look at some of the barriers and enabling factors for EV battery repurposing. Lastly, I'll look at the feasibility analysis for an EV battery repurposing facility in New Zealand. So today it's a pretty relevant topic, and New Zealand has had great uptake of EVs, and another particularly important point is that a large number of those EVs have been imported, so reaching a sort of end of life a lot more quickly than perhaps some other areas, other countries of origin. So the graph on the left, this comes from the China Energy Storage Alliance, and it just shows the accumulated global energy storage by capacity. And you see while the majority of storage is pumped hydro, they have large capacity applications. Electrochemical technologies in the orange are also growing very rapidly. If we then look at, on the right, the electrochemical storage, just look at a close-up of that, you can see that the vast majority of that growth is due to lithium-ion storage, and we've really seen huge growth in lithium-ion batteries, mainly due to the uptake of EVs, which has really helped with costs coming down for that battery. So this table just provides a visual comparison of different established battery technologies, both lithium-ion based, but also other established battery chemistries. If we just look at the top half of the table, these are all the different lithium-based chemistries where these materials refer to the cathode material. You can see there's quite a range, LCO at the top, which is more commonly used for your portable batteries, phones, that sort of thing. The next three, LMO, NMC, these are often blended, for example, for the Nissan Leafs, Renaults. Also, NCA is a common technology used by Tesla in the EVs. And if we look at the next two, LFP, LTO, these are other. And I've also plotted the characteristics, talked about safety, energy density, P over E ratios, the power compared to the energy, the cycle life, round trip efficiency. So what we see, oh, hang on, sorry, on a hair trigger. So what we do, an interesting point to note is that if you look at the safety, so low safety on the left, high safety on the right, you often get this trade-off between safety and energy density. So whereas you have these higher safety ones have much lower energy density. So the second half of the table looks at other battery chemistry such as sodium sulfur, used for kind of large scale battery applications, stationary, vanadium redox batteries, advanced lead carbon, NiCads. But what you look at, if you look at the far right, the table looks at which of these chemistries are used for stationary battery energy storage systems. And you can see that most of those are used for first use, so looking at new batteries for stationary storage, except for the top one, which is the more portable, and Tesla's. Sorry about that. Can I have the? Sorry, just get the mouse. That's better. And then this far right column shows the applications where second use batteries have been used for energy storage, and that's using LMO, NMC, and the LTO. So what's interesting to see is you get quite a lot of flexibility in your lithium-ion batteries. So the next step is what applications might repurposed batteries be useful for, and so this looks at the landscape of the different stationary battery energy storage applications. So after reviewing the battery chemistries, we looked at the different applications, and these can be classified on the x-axis in terms of their discharge duration from seconds to seasons, and power requirements up on the y-axis. So lithium ion can operate basically in this zone here, so quite a wide range from seconds to days. You can characterise these stationary applications in terms of whether they're behind the meter or on grid, and also terms of the applications, whether it's ancillary services, renewable integration and end user. Cheng actually looked at a number of these coloured applications. Due to the time constraints, I'm just going to look at a couple of examples, which is frequency control, ancillary service, and end user using households. So looking at frequency regulation, it's quite interesting to note that when you look at the capacity of global battery energy storage, 50% of those batteries are used in frequency regulation. So this is quite a dominant mechanism, but partly it's due to such large applications. If we look on the right, this is just a graph that was in Transpower's distributed BESS report that they released last year, and it just gives you a feel for how well the battery energy storage can respond to, say, an under frequency event. In blue, you see the response that is by the present system, just with the inertial sort of hydro-based systems. And you can see that the battery energy, the BESS system in red, is responding in hundreds of milliseconds instead of seconds. So globally, BESS for frequency control is quite profitable, particularly in markets like Australia and the US. Looking at New Zealand, it has lower value, perhaps we found, but this is perhaps because it's not clearly regulated to allow BESS solutions. Also, I don't think there's enough reward for taking into account the faster response. But when you look at decreasing inertia scenarios, which are predicted due to high solar uptake, this might make BESS a bit more attractive. So on the right, this is some graphs of some frequency control BESS storage systems that are in Germany. There's two there, a blue and the orange. The top graph, sorry, it's a bit small, but just shows what happens over a year and the frequency, relative frequency of different state of charge. And you can see that it's quite a narrow band between sort of 40 and 60% state of charge. So this is just showing that this has been operated at a state of charge which is conducive to prolonging life for your batteries. So this is quite a good profile for something like a second use application for BESS. The bottom graph shows the C rate that is being used for the same systems. And again, if you talk about the C rate, it's just being operated charging and discharging between about 0.2 and minus discharge and charging of about 0.2 C. So again, these are really a great sort of profile for a second use battery. The interesting point about one of these systems, it was actually used for active spare parts. So if you're storing lithium-ion batteries, you don't really want them just sitting there. They like to be used, but gently. So this is active spare parts. So while these spare parts were waiting to be used for other purposes, they were helping to provide frequency control for this system. So this was a system used by Daimler Mercedes. The second application that we're going to look at that might be suitable is battery energy storage is end user, so householders using for load shifting, if they have flexible price structures, or in conjunction with, say, solar panels to help improve your self-consumption of your own generation. The prospects are that this is going to have quite huge growth globally and potentially large growth in New Zealand. The estimates of behind the meter PV storage go up to about 60% by the year 2024. In New Zealand, battery energy storage still isn't financially viable, but we still see some popularity, partly due to backing up solar and providing some backup for electricity outages. And what we find in this regime, that's again dominated by lithium ion, you can operate these at small energy capacities, which are probably easier for a first pass repurposing system. You can work at quite low P/E ratios, and this is actually the most common application for second use BESS. So figure 8 shows the result of a BESS survey, looking at all the literature for mid and large scale BESS projects, but also some of the small scale projects. So on the x-axis, we've got energy, and on the y-axis power, and this is in a log-log plot. And each of the applications surveyed were put as a dot. Now, just to explain these diagonal grey lines across the graph, they respond to fixed charge-discharge ratios. So the lower half of the graphs here are going from like a C/6 discharge level, so low rates of discharge and charging, up to high 6C. So what we can notice from this plot is firstly the different chemistries are plotted in different colours. You'll see that NMC and LFP are by far the most common application chemistry. The shape denotes the application, so down here a lot of end user, both commercial and industrial as well as household, and the triangles renewable integration, the circles frequency control. But what you do see is also that all the lithium ion batteries, the first 4 of these colours, are dotted all over from small systems to large to low charging, discharging rates to high. So you can see that the flexibility of the lithium ion solutions. Some of the non-lithium ions, such as the sodium sulfur, VRB, are much more restricted to the larger systems at sort of lower charging and discharge rates. The next section I want to look at is barriers and enabling factors for EV battery repurposing. A number of repurposing case studies were reviewed, and what was noticed is that we look at the regulatory and liability barriers. There can be an issue with third parties repurposing EV batteries because, and this is a lot due to the fact that the large battery manufacturers and EVs in China are required to look after the materials from the start to the end. So there's some issues with liability and that kind of thing. So how to avoid that is make sure you have some good collaborations. Best repurposing solutions were working when they were subsidiary companies of these larger EV lithium-ion battery manufacturers. And it's important to avoid separation of rights and obligations for the EV battery disposal. New Zealand is in a position where it has a lack of regulation around e-waste. Hopefully that's changing. I think earlier this year it's been stated by the government that the Ministry of the Environment is going to be developing a stewardship program for e-waste, and then that's going to be one of the first things it's focusing on is lithium-ion batteries. I think in New Zealand we recycle less than 1% of our lithium-ion batteries currently, so we've got a long way to progress. There's also a lot of issues around safety concerns. Lithium-ion batteries can be quite volatile, especially if they're not looked after. There's been a lot of work about certifications happening, the US, China, Canada. So there are standards for how these batteries should be repurposed and what conditions. So we can either gain certifications in these existing or come up with our own regulations. As well as conducting pilot programs is a good idea to de-risk, not only from a regulatory perspective, but also from the technical and economic perspective. So now looking at the economic and technical barriers, repurposing can be quite labour intensive. There is quite a wide variety of battery packs, different modules and cells, as well as the chemistries. One way to optimise, avoid issues around here is to specialise in the battery packs that you're going to disassemble. Also look at optimising your module size. It's less intensive to operate on larger packs or larger modules. However, if you've got defect issues, if you operate, you're going to be throwing a lot more of your modules away if you've got modules with larger numbers of cells. So there is a sweet spot for that. Innovation in battery disassembly will also help with the labour intensiveness. Testing time is a big deal when it comes to repurposing. You need to understand what the state of health of your batteries are as they come in. For some cases, you can have diagnostic data which might accompany. In a lot of cases, that might not be available. Testing time can take anywhere from hours to more than a day, but there's a lot of scope for advanced battery testing diagnostics. There's also the high cost of battery peripheries. By increasing the share of the battery in the total cost, you can keep that share of peripheries down. Obviously, when you're dealing with second life batteries, you've got a concessions in your performance or cycle life. And I've already alluded to that in the previous slides. You want to select applications with battery conserving load profiles. You don't want to be using large depth of discharges, and you want to try and configure for life extending load profiles with the lower P/E ratios. There's interesting things happening in advanced management of technologies. For example, the battery management. Re-Electrify is a company in Australia who are looking at combining the inverter and the battery management in one. They look at the individual health of cells, and they can omit cells if they're not so good, or treat them differently to, different voltage treatment depending on how healthy they are. So there's a bit of feed through here from using advanced management, battery management, to testing to aid repurposing. I'm just going to briefly touch on recycling because it should be noted that recycling can be considered competition to repurposing. It has an influence on the price for your end-of-life first-use batteries. If you're getting a high price for recycling, that's obviously going to lift prices for what you can buy for your repurposing applications. There's also the potential to provide residual value for batteries following second use, which can make it more economic for customers of second-use batteries. This is an evolving technology. There's many process streams that exist. So the graph that I've got here on the right, all the different arrows just refer to different recycling companies. You can see there's quite a variety of different ways for recycling. Obviously for lithium ion, there's a number of different battery chemistries. But what's common is they generally have a pre-treatment stage, which goes on to recycle either using a pyro stage, which is putting them in hot furnaces, physically manipulating the battery to break them down, and also the hydro refers to it uses basically a chemical way to leach out your metals from that. So lastly, just to look at a feasibility analysis. So we did a feasibility analysis for EV battery repurposing in Besa, New Zealand, used a net present value economic analysis, and the base assumptions that it used is that Nissan Leaf batteries generation 1 would be collected, and it used some values from Ministry of Transport statistics and data from Vector, who've looked at what the end-of-life batteries might be coming in the near future from EVs. It assumes that there's about 70% residual capacity for these EV batteries, looks at pricing equipment and personnel. To do this, we used NREL repurposing calculator and customised that for New Zealand conditions. Applied a discount rate of 77%, testing time of 75 minutes, so it's assuming some level of advanced testing or diagnostic information about the batteries that we received. Key was setting what purchase price of the end-of-life first-use batteries were, and this was set at about $10 per kilowatt hour, and that's because in the New Zealand context currently we don't have much of the way of recycling happening here. People that are buying old EV batteries are doing so either making people pay to take them away or getting them for free. So there's not a big price there at the moment, although this could change in the future. The selling price was calculated by looking at what currently repurposed batteries were selling locally in New Zealand, and also by looking at new EV battery prices and new BESS systems we're going to be selling, and looking at that for the next sort of 5 to 6 years. Note that the battery prices are expected to decrease over time, so this was reflected into the second use price that was used in the calculation for the MPV. So I think it used a 10% reduction on each year. So if we look at the graph on the right, if we just focus on the baseline case, which is what I've described here with the black circles, this shows for this scenario you can actually get positive MPV happening by about 2025. Obviously there's a lot of uncertainty and unknowns, so some sensitivity analysis were conducted based around this base scenario. So fewer batteries, the number of batteries was assumed to be collected was in year 1, 40 to 530. This lower curve here for fewer batteries, that was assuming about, I think, a third or a fifth of that amount. And again, higher batteries also has a much bigger impact on the NPV. So I think that was using a scenario for all North Highland EVs. As we said, there's a bit of uncertainty around the purchase price for end-of-life first-use batteries. We've assumed 10, but we've also looked at annual increases of the battery purchase price, either $1, $2 or $5 from the base price for these here. And you can see that it's quite sensitive. We're still getting into positive NPV territory at $2 or $1 increase per year, but not when you get to 5. Longer testing time is also critical. We said that was the 75-minute testing time is making an assumption about advanced techniques or having some pre-knowledge about the state of health when you get it. If you add in a 12-hour test time, again, the NPV goes negative. So just to conclude, so the lithium-ion chemistry is expected to dominate the BESS market in the foreseeable future. The good news is that EV battery repurposing should be facilitated by a stable environment. We don't see any imminent threat from newer substitute technologies coming along anytime soon. Lithium-ion chemistry is suitable for a range of BESS applications. EV battery repurposing can be further facilitated due to application flexibility. I think for an initial application, the end user household style repurposing looked to be the best option. EV battery repurposing was shown that it could break even within quite a short time span. And as I said, the second use BESS is particularly suited for load shifting applications. However, while it's not economic at the moment, we can show a cost advantage over first use BESS. And we recognise that there's a lot of external factors which will impact the viability of BESS profitability here. Okay, so if anyone's got any questions, I haven't.
Thanks very much, Cherie. Again, if you have questions, please post them in the Q&A panel. Cherie, while we're waiting for questions, I've got one for you. Is there any indication that vehicle manufacturers are considering second life applications in their design and production?
I don't know. There's a number of manufacturers trying out trials. Nissan, for example, is working with Sumitomo, and so there's a lot of interest in repurposing. I'm not sure if they're altering their manufacturing to make it easier, but that would certainly help. At the moment, there's just a wide variety in battery formats, both the cell formats, module formats, and chemistries. It really looks like it would be quite a difficult proposition to just randomly use any battery pack from any vehicle.
Yes, I imagine it's a rapidly evolving space as well, of course.
Yes, yeah.
Cool. All right, we don't have any questions coming through, so thanks so much, Cherie. I'd like to just move on to closing out the seminar. Just like close by saying the EEA is looking for your feedback and looking for ways to improve the seminar series. So you will have received a short survey, so please give us your feedback so that we can improve our future events. I'd like to really make special thanks to the presenters today, Eric Walters, consultant, from Wu, from Transpower, and Cherie from the Epicentre. EEA would also like to make special thanks to the Epicentre, in particular Isabel Lequelec and Dr. Radnya Makadar for your support and organisation of all this. And also thank you everyone for registering and being a part of the EEA, being a part of this event. Without you, we're really unable to run these sorts of things and produce this high quality dissemination of information and guidance. So with that, I'll close the seminar, and until next time, thank you very much.